In this video, I'd like to go through some examples of some special functions so that we can find their Taylor series centered at 0. And then as we move forward, we're going to want to look back to these when we start to, again, expand the types of functions for which we want to find Taylor series. We so far have seen the Taylor series for the function 1 over 1 minus x. And I'll also note here that I am specifically focusing on x, the center being at x equals 0. And that doesn't mean we won't see Taylor series that are centered elsewhere. In particular, we'll get some practice of that with class. But I will say that the center being at 0 is very common, and so we will end up being able to use these centered at 0 quite a bit. The key thing, though, is the practice that we're going to get and the process of how I find the coefficients and then get into the pattern so that I can put it into sigma notation. So for the function e to the x, again, I'll just as a reminder, our formula is, because each of these are centered at 0, we're having terms that are the kth derivative of f at 0 divided by k factorial times x minus 0, or x to the k. So in each of these examples, what we need to do work for is figure out what to put in here. Now, for e to the x, we still have, as we've observed before with our Taylor polynomials, the advantage of knowing that for this function, any derivative is going to be e to the x. And consequently, if we evaluate any derivative of this function at 0, we're always going to get 1. It's e to the 0. What that tells me is that the Taylor series for e to the x that's centered at 0 is summing from k equals 0 to infinity. We're going to replace the green box with 1, and so I'm just going to get 1 times x to the k divided by k factorial. The second part of this example is asking us to find the interval of convergence in each instance. So to do so, we want to use the ratio test. And if I use the ratio test here, I'm going to take x to the k plus 1 divided by k plus 1 factorial. And then I'm going to divide by or multiply by the reciprocal then of the kth term. This allows me to bring out the absolute value of x. And what remains is the limit of k factorial over k plus 1 factorial. But recall that we can simplify that ratio to just 1 over k plus 1. Again, I can drop the absolute values because I know that I'm dealing with positive k values. And this limit goes to 0. And that's always less than 1. So what we're finding from this is that the ratio test tells us that this converges for all x. So that means that the radius of convergence in this instance is infinity. And consequently, the interval of convergence is minus infinity to infinity. So that is actually pretty powerful. We're saying that unlike the 1 over 1 minus x Taylor series, this Taylor series converges for any x that we might choose to plug in. Next one I want to look at is the function natural log of 1 plus x. And again, still assuming that the center is 0. So here I don't have an obvious idea of what the derivatives are and what the pattern would be. So I start here with my function. And we're going to plug in the center 0. Now in this case, natural log of 1 is 0, so that first term evaluates to 0. Then f prime of x is going to be 1 plus x raised to the minus 1. If we replace x with 0 there, we'll get 1. The second derivative is going to be negative 1 plus x to the minus 2. Evaluating at 0 yields negative 1. And I'll point out my intent here is that I don't have a known stopping point because we're we're not finding an nth degree Taylor polynomial. So my hope is to find enough of these so that I can observe a pattern for the numerical values I'm getting as outputs here. So the third derivative will be positive 2 times 1 plus x to the minus 3. Evaluating at 0, we'll end up with positive 2. And then if I take the fourth derivative, we'll get negative 6 times 1 plus x raised to the minus 4. Plugging in 0 gives me negative 6. So what I'm starting to observe here is that if we ignore the first term being 0, which doesn't really fit our pattern, after that the terms appear to be alternating in sign, and I can start to associate these to factorials. So this is negative 3 factorial, positive 2 factorial, negative 1 factorial, positive 0 factorial. So after this point, so what I'm observing is it appears that when k is greater than or equal to 1, taking out that k equals 0 case, if I were to evaluate the kth derivative at 0, I'm going to get, it looks like, k minus 1 factorial. And to be clear, why am I putting k minus 1 and not k? In each of these cases, I'm trying to figure out what the derivative number is. So here, k was 4. We were taking the fourth derivative. But we didn't get 4 factorial, we got 3 factorial. So that's why I have k minus 1. And then the other thing we have to make sure we account for is the alternating sign. So there's some negative 1 to the k, or say negative 1 to the k plus 1 or k minus 1. The way I decide is I just need to make sure that the appropriate sign is applied to the appropriate term. So notice that we got a negative when we had k equals 4. So an even value of k caused us to get a negative. So I need to either put k minus 1 or k plus 1 up here. It doesn't matter, because that would give me the same kind of negative pattern. Once I find this, now I want to go back and remember that's what we plug in for the green box here. So the Taylor series, is, so first of all, we're going to put in this up top. We divide by k factorial, and we multiply by x to the k. You'll notice that I paused here because remember that this pattern we found was only true for k greater than or equal to 1. So while the definition does require that I put 0 there, I'm actually going to write 1. So what's happening is you could imagine that we have the k equals 0 term added to this, but the k equals 0 term is just 0. So we can just completely skip it in this case. We can simplify this because this ratio simplifies to 1 over k. So we end up getting the sum from k equals 1 to infinity of negative 1 to the k plus 1 times x to the k, all divided by k. So that is our Taylor series for the natural log of 1 plus x, centered at 0. And then recall the second part of this question was find the interval of convergence. So if we take the series we just found, which let's put it back into view, and apply the ratio test to that, I'm going to disregard the negative 1 to the k plus 1 because of the absolute value bars, and see that I'll get x to the k plus 1 divided by k plus 1. And we're going to multiply by k divided by x to the k. Again, I can factor out an absolute value of x. And we're left then with the limit as k approaches infinity of k over k plus 1. That limit goes to 1, so the limit results in just that multiplier out front of the absolute value of x. And so the ratio test implies that the series converges when this is strictly less than 1. this limit, which we said was absolute value of x. And the structure here is telling us, again, that the absolute value of x minus its center must be strictly less than 1. So this is a way of indicating that the radius of convergence is 1. Our center is 0, so our endpoints naturally are going to be -1 and +1. And we need to check and see if we actually get convergence at either or both of those points before I can explicitly write down the interval. So if we plug in -1 to the sum we found above, we're going to get, oops, fit it in here, the sum from 1 to infinity of -1 to the k plus 1. And then x to the k now becomes -1 to the k. But we can simplify that. We have -1 to the k times -1 times -1 to the k. But -1 to the k times -1 to the k is always going to be positive. So what I'm observing here is this numerator is -1 to the 2k times -1 to the first power. That's just -1. So we're just going to get -1 over k for these terms. This diverges. It's the negative is you can factor out, but what's left is a p-series where this p-value is equal to 1, the harmonic series. If I plug in 1, then the x to the k part just becomes 1, and we're left with this series, which is alternating. So we can check our alternating series test conditions. 1 over k goes to 0, that's true. And 1 over k plus 1 is less than 1 over k. So this tells us that this series converges by the alternating series test. So what that means is that this is our Taylor series, and the interval now, we know the endpoints are -1 and 1. Now what we've found is that we get divergence at the left endpoint and convergence at the right endpoint. And then finally, the last kind of classic example I want to go through here is cosine of x. And again, centered at 0. So we're going to have our original function. When we evaluate cosine of x at 0, we get +1. And then the first derivative would be minus sine of x. Evaluating that at 0, we get 0. Second derivative is minus cosine. Minus cosine of 0 is -1. And the third derivative is positive sine of x, which evaluates to 0 at x equals 0. Now, what I know here is that this is going to repeat. So I can see that I'm going to get 1, 0, minus 1, 0, 1, 0, minus 1, 0, etc. for my pattern. So I can stop here and then think about how I can try to express the Taylor series. One of the things that's difficult is we have a situation where every other term is 0. So if the coefficient is 0, then we're not going to include that in there. And so I have to figure out how to write that in sigma notation. Well, if we think about the way that the Taylor series is expressed, we're going to, again, think of our coefficients as the number we're finding here divided by k factorial times x to the k. Well, let's start to write out some of these terms. So the Taylor series, and my goal is to put this into sigma notation, but the Taylor series, well, the first term is just f of 0. And then we would have plus 0 times x to the first power minus 1 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth plus 0 over 5 factorial x to the fifth, etc. So what's happening here is I can just completely disregard the odd exponent powers of x. the odd powers of x, that's what I should say. And we're left with trying to express 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. in sigma notation. Notice that it looks like, first of all, we want the exponent to match what we're taking the factorial of. And instead of writing k, because I don't want to have odd k's, what if we put that as x to the 2k and then match that with 2k factorial on the bottom? It turns out that this is going to be a standard kind of trick to make it so that you only hit even values when you want to write sigma notation. And then the last thing I have to consider is, what about the sign, right? There appears to be an alternating sign. First of all, I've got to fill in that exponent, but I should say, to get that first term of 1, we know we want k to be 0, starting value of k. So finally, what I'll do here is note that I want the first term to be positive, and that would happen at 0 if I write -1 to the kth power. So it turns out this is our Taylor series, and we finally want to find the interval of convergence as well. So I can use the ratio test here. And in doing that, we will get, again, I'm going to ignore the -1 to the k. When I replace the k's with k plus 1s, I have to distribute the 2. So this will be x to the 2k plus 2 over 2k plus 2 factorial times 2k factorial divided by x to the 2k. This is going to allow us to bring out an x squared from the limit. And I now want to simplify this ratio. And recall that what will happen is we can cancel the 2k factorial, by recognizing that the factorial in the denominator can be expressed as 2k plus 2 times 2k plus 1 times 2k factorial. So that would cancel the factorials from the top and the bottom. And we see that the limit of what I have left over here is always going to be 0. And so much like the example we saw with e to the x, this tells me that the radius of convergence is infinity. This always converges. And then consequently, the interval is the whole real line. So there are 2 more kind of classic functions that we'll want to know the Taylor series centered at 0 for. And we will see those soon. I'm not going to go through those here. We will do one of them in class, and the other one we'll be able to come back to later after we fill in some more information about Taylor series.